Finally, and it is continuing the second quantization. It is quantization of the field. Quantization of radiation field. And the initial state of electromagnetic field. The initial state is that many particles has specified k and lambda, and the first particle and the second particle k2 lambda 2, and like that, and n particles in arbitrary, and n k anyway, and the ki or the lambda I, and plus, and so not plus, and so many particles, and so many particles in each, and the ki and the lambda I mode, and here n is that number of photons with ki mode. And the two each state are orthogonal because they have the same number of photons in each mode. So, and it is initial state. Initial state is that each photons have their specified and the momentum and wavelengths. But the final state of electromagnetic field, and here after the observation, observation of one photon in the k lambda mode, and when the electromagnetic wave, like a photon, one photon is observed by the matter. So in this case, n k1 lambda 1 and k lambda 2, like that, and also in general, n k lambda minus 1. This photon with k lambda mode, this one photon disappeared, the other preserved, and it is observation. And in this case, and transition, and let's think about that transition rate. Transition rate from one initial state to final state. And initial state, and it is initial state is that here ground state, and n k1 lambda 1 and k lambda, and so many particles at the ground state, and the final state, and the energy level excited at the n energy level, and n k1 lambda 1 and n k lambda, one photon observed, like this. And the transition rate from the Fermi-Golden rule, transition rate from the initial to final state, and here is coming from the Fermi-Golden rule. and the transition rate gamma in the ground state to the excited state, it is that the 2 pi over h bar, and final state n k1 lambda 1 and k lambda minus 1, it is a final state, and the interacting Hamiltonian and the initial state 0 and k1 lambda 1 and k lambda, like that. It is a square. It is a Fermi golden rule. Fermi golden rule is it is the initial state, interacting Hamiltonian, and final state square, and the 2 pi over h bar. That is the Fermi golden rule. It is a transition. It is a transition rate. That is a transition rate. And also here, another thing is that multiplication with the delta function, and the En minus E0 is that minus h bar omega. That is that here 1 photon. Final state is that E0 plus h bar omega. Here 1 photon observed, and also there is a transition rate here. So then we already know that the interacting Hamiltonian and from the definition of the interacting Hamiltonian, we already calculated minus E over C volume integration quantity density dot A R plus E square over 2mc square, and rho R and A square RT. Then actually, and this term coming from the diamagnetic part. And anyway, then E is the elementary charge, and C is the speed of light, and also this value is very small comparing to this first term, and also A square also very small. So it is negligible. So we can neglect this term, and it is we can neglect this term. It is the diamagnetic part. Then also from the definition of the current density in the quantized expression, and the E of C, and the volume integration JR dot summation K lambda, and the square root 2 pi h bar c square of omega. Then this one is is a definition from the normalization factor. And also here A k lambda epsilon and k lambda, and also here let's divide by the square root v, that is volume normalization, and exponential I k dot r minus omega t, and also it is a complex conjugate, that is A vector. So, and from transition rate means that the absorption or the emission here it is complex conjugate here minus E of C summation K lambda and square root 2 pi h bar c square of omega, and this basically this volume integration with J, and also here there is an delta function, so you can make that here A k lambda and the current density minus K, and the epsilon K lambda, and the 1 over square root V, here volume integration volume integration coming from the normalized. So it is that the exponential minus I omega t only. And plus complex conjugate is that the a k lambda dagger and the j k and the epsilon star k lambda and the square root v and the exponential I omega t. Then the physical meaning of this one is that here it is this term is that it is photon. It means that the photon annihilation photon annihilation means that it is absorption, and it is a photon creation. Photon creation means that it is emission with matter. So interacting Hamiltonian means that by applying the electromagnetic wave like photon irradiation, in some cases, and observe the photon, in some cases emission of photon, and during it is not a reflection but quantum mechanical energy transfer or the from the transition rate, Fermi-Golden rule. So then here absorption or the emission of light can be calculated from this expectation with the initial state and the interacting Hamiltonian and the final state. So we should calculate this one, and this square means that is Fermi, it is the transition rate. So then let's think about that. First case and the absorption. Absorption in cases, and the final state is n state, and also n k1 lambda 1 and k lambda minus 1. It is observed, and interacting Hamiltonian, and the initial state is ground state, and k1 lambda 1 and k lambda in like this. And here it means that here it is a ground state and excited state by observing photon with a k lambda with interacting Hamiltonian, and it photon observed, and it makes photon observed, and it makes that excited state, and the initial state is a 0 and k lambda in general, and only think about it, and also and here n state, final state is n state, and also n k lambda photon observed. So and number of photon disappear. One photon disappeared from the observation. So here mathematical calculation is that minus e over c square root 2 pi h bar c square omega v, and the summation k lambda and n j minus k vector dot epsilon k lambda in 0 and k lambda minus 1 and a k lambda t and k lambda like that. And here it comes from this nk lambda, ground nk lambda expectation with the annihilation operator, nk lambda, and multiply the annihilation operator, and it becomes that nk lambda observed photon. And also energy cases operate with the current this current is that is kind of a velocity, energy velocity, so it is applied to the energy term. So and also multiply then it is absorption. So from this we can calculate the transition rate. Transition rate with the ground state to excited state from the observed state is that 2 pi over h bar, and also square of this one, and correct delta epsilon n minus epsilon 0 minus h bar omega, and final state and interacting Hamiltonian and initial state equal to E square. Then it makes that from the above relation, square is that here 2 pi and 2 pi and 4 pi square and E square and c square cancel each other, and omega v, so it is 4 pi square E square over omega v, and here this is annihilation operator. It makes that annihilation operator makes that nk lambda minus 1, that it is orthogonal. It is from the normalization factor, it is 1, so only this one. So here nk lambda and j minus k dot epsilon k lambda and 0 n square, and also Planck delta epsilon n minus epsilon 0 minus h bar omega. So, and here we calculated from this one is that from the creation or annihilation operator is that square of n k lambda and n k lambda square, then it is n k lambda. So it comes from here. It is when you apply this, it is a dagger. So because we already know that here a dagger n k lambda is that square root n k lambda plus 1 n k lambda plus 1, and the annihilation operator k lambda n k lambda is that square root n k lambda and n k lambda minus 1. That is from the creation and annihilation operator like this. That is the transition rate is like this. It means that from the one photon observed and excited from the ground state to the excited state, and one photon observed. So here it is expectation of the energy current, and energy current for each polarization direction. And also second case is the emission. Emission of light is that here emission ground state and excited state, and from the excited state and ground state and photon observed, and the k lambda photon created, so and the ground state is that 0 and n k lambda plus 1 photon created, and n k lambda and the photon created. So in this case the emission from the excited state to the ground state, the photon is emitted, and then the 2 pi over h bar, correct delta epsilon n minus epsilon 0 minus h plus h bar omega, because in the final state is the epsilon 0 minus h bar omega. So, and also multiply. The final state is 0 and n k lambda plus 1, and the interacting Hamiltonian, and the initial state is n like n k lambda and square. And that is the transition rate. From this transition rate calculation, the result is that the similar, it is 4 pi square e square over omega v, and here n k lambda plus 1 and 0 j k dot epsilon k lambda n square, correct delta epsilon n minus epsilon 0 plus h bar omega. Because this creation operator here, it means that it is a creation operator, and the final state is n k lambda plus 1, and the initial state is n k lambda. So, and here it is a creation operator. It means that I will write down in more detail. Is that final state is 0 and n k lambda plus 1, and a k lambda creation operator, and n k lambda square, then it is that square root n k lambda plus 1, n k lambda plus 1 and n k lambda plus 1. So it is n k lambda plus 1. So it is emission of light is coming from the excited state to the ground state. One photon makes that k lambda mode photon created. Anyway, then from the here finally, and I will describe for the selection rule. Selection rule with a brief introduction. So, selection rule case, and we should calculate only is like this term J, and initial it is emission case. So this vector potential can make a commutation relation here. It is that 1/2 because J can be write down 1/2 summation I m 분의 pi of m exponential minus I k dot ri plus complex conjugate. Then actually, and from the momentum is that m r dot, then it is from the commutation relation, and m over I h bar and r and h0 from the commutation relation. So we apply this, and this one makes that 1 of m and 0 and here momentum, canonical momentum, and n. Then it makes that 1 over I h bar 0 r h0 n. Then it is 1 over I h bar 0 r h0 minus h0 r n. then 1 over IH bar, then it is epsilon n. It is applied to the n, it is applied to the 0, and it is applied to the n. So, epsilon n minus epsilon 0, 0, r, n. So it is that minus I omega 0, r, n. In other words, it is minus I omega. It is, we call it is a dipole, electric dipole, ON. Here it is a dipole, electric dipole here. Then from the angular momentum expectation, like selection rule means that here delta m should be 0 or the plus minus 1. Because here it is very important. It is very important. And also L prime, M prime, and LG and here we obtain this commutation relation with the R, with the Hamiltonian, but this also can make that angular momentum and LG and RG angular momentum. Then here it is that H bar M prime minus M and L prime M prime and RG Lm should be 0, and it means that for m is not equal to m prime, and magnetic quantum number is different, then L prime, M prime, and RG and Lm should be 0. Then it means that, and also let's only consider for the this commutation relation here. Let's calculate. In other words, then from this commutation relation, and also here L prime, M prime, and it is from the Li, Rj is that IH bar epsilon ijk and Rk from the quantum mechanical expression. So, and Rg, Rg, it means that here IH bar Ry Lm. Then when you compare to this, and this one and this one, then it is this one is that minus I M prime minus M and L prime, M prime, and Rx, Lm. And in here, it is Rg equal to 0, but here from the other expression, in general case, here it is. I do not calculate in more detail here. Then I will write down the result. Then IH bar RY makes that this kind of relation. So it is the first relation. The other second relation is that L prime, M prime, and LG RY commutation with LM is that from this calculation H bar M prime minus M L prime M prime RY LM, but it is minus I H bar L prime M prime RX LM. So it is a second relation. It is a second relation. It is second, and it is first. From this, L prime, M prime, and RX LM is that I M prime minus M L prime M prime RY LM. Then it is M prime minus M square L prime M prime RX LM. So it means that L prime M prime RX and LM should be 0 for M prime is not M plus minus M plus minus 1. So, and it is a selection rule. Selection rule is that delta M, magnetic quantum number difference, should be 0 or the plus minus 1. That is first selection rule. Likewise, in the orbital case, and delta L should be plus minus 1 also. Then it is another selection rule, but I do not derive it this time. So, and basically when you think about the electric dipole interaction, then the transition, we already calculated the transition rate from the absorption and the emission in general case, and this we should remind that delta M should be 0 or plus minus 1, and the delta L is only plus minus 1 it is permitted. Otherwise, it is the probability of the transition is not possible.